Like this effect? Wish you could make it? Well, in this mini course, we're gonna get you one step closer to actually making that a reality. My name is Matt Sola, and on this YouTube channel, I learn and I teach destruction effects in Houdini and Unreal Engine 5. So, if that's of interest to you, like, subscribe, and leave a nice comment. These things go a long way and help me help you. With that preface, in my own mind, I think I have come up with a 7-step system or workflow for creating destruction effects. And let me take you 3 years ago when I started learning Houdini. The program felt absolutely treacherous to learn, completely brutal. It was so hard that I think I tried to learn it like five times. And still I'm learning it on a daily basis. And there's really much better artists than I am, but I think I'm in a position to put my struggle that I struggled 3 years ago into easy to follow methodology that newcomers and even intermediate artists, hobbyists can follow to create such a destruction effects you see on a screen. And I'm gonna guide you through them right now. This destruction effect you see on the screen is for an inspo. It's an inspiration that we can achieve these effects if we put our work and we put our dedication into learning this craft. And on this video, and today, I love to say that we're not going to learn Houdini in one day, but we sure can get one step closer. So, with that nonsense away, the first step with destruction simulations is base geometry preparation. In a single sentence, we are preparing our geometry or 3D asset so that it is simulation ready, so that our solver can take in all the data and spit out a result. So that's step number 1 in this methodology. Step number 2, let's give a Houdini time to think here, is fracturing. Let me zoom in on this mesh so you can better see what we're talking about. And what fracturing means is splitting object into believable chunks. You see these lines? And actually I can initiate my pen to further get this idea across. So you see these little lines that go all across the geometry. It's left, right, on the sides, pretty much all over the place. The whole geometry is encompassed with these different fractures. So that's what the second step is in this methodology. It is fracturing right after the base geometry preparation. Absolutely vital step that we get it right. Okay. Moving away from fracturing, the third step is clustering, and you may have heard about that before. Let's give Houdini time to think. We're working with heavy data. And what clustering is we're taking the pieces that we fractured previously and we're developing a sort of cluster system that sticks smaller pieces together with other smaller pieces or bigger pieces with another bigger chunk. So let me show you what I mean by this. So see this piece right here? It is a one big chunk. Another one? Well, let's look at this one. Big chunk, another one right here. So we have one chunk right here, second chunk right below, and the third one right in the middle. And this is clustering, and clustering is vital for believable destructions, ones that feel realistic, ones that really seem to be polished and nice to look at, really. All right, we know the step 3. The fourth step in our system is let's give time in Houdini for it to think, is constraints. And you're looking at these weird white lines and you're asking yourself a question. What is this spider web? Well, these are constraints. And what constraints are is basically a relationship between each fractured piece. We need to tell Houdini somehow how he should interpret the relationship between each and every piece. Because when we fractured the geometry and we have these different pieces scattered along the geometry, Houdini doesn't really know which one should belong with what. How do they gonna behave? Is it gonna be like should it explode right after, or should there be some spring-like behavior, or should there be more elasticity? And that's what constraints are all about. Constraints tell Houdini about the relationship each fractured piece of geometry has. So that was step number 4. Moving down the chain is impulses and triggers. Now, you might already guess where we're going with this one, and I have prepared an example here. So, when we talk about impulses and triggers in RBD destruction simulations, what we're actually referring to, actually let me get a better view here. And what we're actually talking about is the trigger points, or not trigger points, but triggers or like impulses that going to build a cause and effect. So obviously in real world, to destroy something, we need something. Either we take a bat and we swing onto something, we take other things or other means of how we can destroy something, and the cause makes the effect. And similarly, in Houdini, we have to replicate this. There has to be some kind of force, some kind of impulse or a trigger that's going to go either through the geometry or other means that's going to destroy the geometry we have. And we're going to look at this in a second. So, right after impulses and triggers have been made, we go into the step number 6, which is simming. And I have a sample here we're going to look at. You have this little ball, which is basically an impulse or a trigger, and we feed all of the data into the RBD bullet solver at the step number 6. And what happens is, let me play this, a destruction suddenly happens. Well, it's because upstream, and let me zoom out, upstream, and let me pause the timeline here. I'm going to initiate the driving mode, because upstream we have ensured that it comes into the bullet solver. And you see I have created this little pinkish color, and actually a bullet solver has this sort of brain the color, also an icon, which cleverly indicates that everything we have created up until step 5 is going to join into the simming stage, and Houdini's bullet solver is going to look at the data, is going to interpret it, and is going to return us a destruction. And that's what simming is. It's basically the brains that think about, thank you for pulling this data in, I'll try to understand it and give you a destruction. All right, we're getting somewhere. Can you guess what the final step is? Obviously you can, because it's on the screen, and that is caching. Now let's look at caching. And you saw just a moment ago, I had viewport issues. When we play through the animation, we can see that it's a little bit laggy. It's not as responsive. There's missed frames and things like that. And that's why caching your geometry is so important. In simple words, it means instead of using my computer's processing power and available RAM, instead what I will do is I will take all of the Houdini's data that's inside of this destruction. I'm going to take all this and I'm going to pull it onto the hard drive or an SSD, and I'm going to empty out my RAM. I'm going to leave my processor alone. And that way, we're no longer processing the geometry, and as a result, we're gaining a much higher frames per second. The viewport is going to be more snappy and responsive, and our computer is not going to crash, especially if we're working with lower-end systems, because these destructions are heavy on our computers. So, let me pause the simulation here. So, let's look at this once again from the top down. Step number 1, again, we prepped our geometry so it's simulation ready. We fractured into smaller pieces. We clustered the effect so it looks more believable. We created a relationship between each and every of those pieces, so the solver understands the relationship, how they're going to move. Are they going to be elastic? Is there going to be elasticity? Or is there going to be rigid as a one piece? And we're going to look at that in a moment. After that, we add some kind of an impulse or a trigger that's going to initiate this destruction. Step 6, we pull all of the data upstream that we have worked up until this moment. We connect it into the bullet solver and let it do the job. And inside this bullet solver, there's multiple settings that we can look at that are vital to how this plays out. And finally, we take everything and we export it on our hard drive, so we're not going to have to deal with all this heavy geometry. Okay, we're learning something today. What do you say if we take a closer look at the base geometry preparation and how we can take this? Actually, let me take the flag off, zoom in, and how we can take this geometry that we see on the screen and how we can start to think about these preparation techniques. You know, what are these things that we actually have to do for the geometry to be simulation ready? Let me dive in and we can take a look at it right now. And I'm going to initiate my drawing tablet here. And for me to better illustrate, I have created multiple demonstrations. And we're going to go through each and every one. And I want to know that if you don't have enough time today to go through the whole video or this mini course, I want you to bookmark this course in your browser and come back when you have free time, because I believe I have laid out everything that I have learned in those last 3 years. And I believe you're going to take away a lot of good lessons that are going to help you create believable destructions. That said, let me zoom in. And you can actually take a moment to read what base geometry preparation means. Okay? Now, let's look at the first example. I have dropped down a file node, and what the file node does is it allows me to import a geometry from any application. And it could be Blender, it could be 3ds Max, it could be Maya, Cinema 4D, what have you. I drop down a file node and import my geometry from 3ds Max. And I chose mine by clicking on this little icon, if you want to follow along. And when I do so, the geometry basically appears in my viewport, but immediately we can see there's a bunch of issues with it. The first notable is obviously the shading. And let me initiate the drawing tablet. We have these weird black lines or shadows appearing on our geometry. Well, what's the deal with that? Well, that's going to be the second point. But the biggest problem right now is if we look in our viewport, we can see that our geometry isn't even centered. It's somewhere into the oblivion. So we know that our center of the viewport, or our 3D space, is here. So here are the zeros, and this has completely different position in space. So that is a huge issue, because it's going to give the RBD bullet solver a huge headache, and that can cause all kinds of different problems. And the bullet solver is going to have a trouble returning an accurate simulation. It might not happen on simple shapes like this, but if you're working, imagine huge towers, okay, or anything, or bridges, or anything like that. And if this is positioned somewhere, nobody knows where, and we try to, oh yeah, RBD bullet solver, take this, try to figure it out, it's going to say, well, I'm not really understanding how should I add my forces, how should I add constraints. It's going to cause all kinds of different problems. Before these problems even happen, what we want to do is we want to take this geometry and we need to reel it back in. Because look, if I click Control middle mouse on this file node, I can see that the position of this box that I have imported is 119 units in X, 200 units into Y, and minus 47 into Z. So wouldn't it be neat if I could negate each of these values so that I can reel it back in? And we can actually do that. If we take negation on each of every node, the geometry theoretically should come into the right space. So to do that, I know that I can use a node called transform. And if I hover my mouse over this part of the screen, tap tab, and write transform, and sure enough, here it is. I can choose it from the list, and there it is. When I click P on my keyboard again, it's going to open up a node settings, and we're going to use a clever function that Houdini has, and I'm going to actually click Alt-click on the translate. Oh, sorry, not Alt-click, but Alt-E. And when I do so, it's going to pop up this little box that I can use to write in any function that I know or even don't know. We can search for that online, we can search on that on forums, whatever the place you have. But I have learned this little function that is going to take those values that I just showed you and is going to negate them. And in return, the geometry theoretically should go back into the zeros. And when I put my display flag on this node, sure enough, the geometry is centered and ready for simulation work. So that is position and orientation. Absolutely vital that we have this set correctly. It has to be always in the center of our viewport. Next one we have to deal with, we just saw the normals, right? Actually, let me put the display flag back onto this. These black nasty things, I mean, they're hard on the eyes, right? Not something we want. Whenever we see this stuff on the geometry, is the first sign that either the points are not welded or there's something wrong with either geometry or the normals. And in this case, it's about the normals. How do we fix this? Well, we need a better normals. How we do that? Well, there's a node in Houdini called normal. And if I press tab on my keyboard, it's going to open up our node menu, and I can type in normal, Normal, And sure enough, there's a node called normals. And if I let go of my mouse, I can plug this in on my file node, bypassing this one, actually, and it's basically going to solve the problem for us. We're generating new normals so the shading looks correctly once again. I'm gonna get rid of this node because I already have it in the scene, and you'll see that I have annotated each and every node that it helps us read the network better. So this node imports geometry into the Houdini, and the normal node creates surface normals for us. I mean, you can probably read, and I'm not going to read this on every node. Next example is grounding, very similar to getting our geometry towards the center, but grounding is a little bit different, but absolutely vital for getting our geometry ready for simulation work. So I'm going to put my display flag on this rectangular box, which resembles a wall, and whenever we do simulation work, not only is it important to get our geometry at the centers, but it is also absolutely vital for our geometry to be flush to the ground. You see? Right now, we have a positive direction, which is shooting up here, which is in y, which is a plus y. And we have a negative value that is pointing into the negative minus y. And what we need to do is we need to take this minus y and push it flush to the ground. How do we do that? Well, there is a node which is called match size node, and this node that you see here is often used for solving problems like this, aligning geometry to however you want it. But this time we're going to use it for making our wall flush to the ground. I'm going to select the node, put a display flag on it, and what it does, it makes our geometry flush to the ground. How did I do that? Well, how about we look at it? P on my keyboard to put up the settings, and there's a setting right here. I'm gonna put a rectangular box here, and I'm going to choose minimum, and minimum actually means this part right here. You know, as you see, this bottom part. I want the minimum to the same. And actually I can do like minimum, I can do centers, or I can do maximums, and that's going to give me all kinds of different results, but not something I really want. So what I want is flush to the ground. Okay, how do I do that? Just the same. You do this, and voila, your geometry is flush to the ground. And grounding is absolutely vital. So let's recap what we have learned so far. We have understood that we need our position and orientation set correctly. Our geometry must be centered in the world space. Second one is normals. Actually, normals are here. Shading errors, things like this. The first thing you see this, you know there's a problem with the normals. How you can fix it? Add a normals node. Next one, grounding. It's not enough for our box to sit in the center. What we need to do? Flush to the ground. So we use match size node, and we have our objects flush to the ground, which are simulation ready. Next problem that we might face whenever we're dealing with the geometries. Let's put a display flag on this box node. And this node creates a rectangular box for me. And actually, let me back up, because I'm going to actually put this flag here. Oh no, and I want to sort of talk you through this whole thing, what water tightness means. Okay, well, watertight mesh means that each point that happens to be on this mesh is welded to each other. So there is no gaps in the geometry. So the way you can think about this, if you're gonna pour a lot of water inside this geometry, okay, from the top, we put a bunch of water in. Is there going to be any places there's going to be a leakage? Is going to empty out? If it does, it means that our mesh is not watertight. And for RBD simulations to work correctly, it is of paramount importance that the mesh is watertight. It is closed and it is not open. So it has to be a one piece. How do we do that? Well, we create our geometry, whatever the geometry is. We use our match size node, again, to get it flush to the ground. Then we use a facet node. And right now I'm using facet node to visualize the problem. So let me drop down a RBD, not RBD, but exploded view. And what exploded view node is going to allow me to do is going to pull my pieces apart, and we can visualize this problem a little bit better. Now you see it. There's a problem. The mesh is not watertight. The points are not welded. See? And I can visualize this with an exploded view node. And cleverly enough, I used facet node here to, actually I'm going to put the menu up. And I used this little check mark that says unique points. See? And when I click that, the geometry is back to where it was, so which is good, watertight. And if I click unique points, what Houdini does, it splits those points apart, and we don't have no longer a watertight mesh. And I'm using this just to illustrate the problems you might have whenever you're importing geometry from other applications. Maybe you created a model, but there's some welding issues, things like that. So the next question now is how we can solve this problem. Is there a node? Is there a method that we can employ to fix this for us? And there is. And it's done by a node called fuse. So I'm going to put my display flag to the fuse, press P on my keyboard to get the menu. And there's a setting called snap distance. And we can choose any snap distance we want until it snaps our points together. And if I click on this display points number, we can actually see that we have different points in our space. Okay, we have 0.2, 3, 1, 0, and so on. And we're using a fuse node to fuse these points together so our mesh is watertight. And you use this whenever you know that your mesh is not watertight and you need to solve this problem. And sure enough, if I use exploded view to pull my pieces apart, we no longer have that. And if I bypass the fuse node, the problem appears. So we want to fix that and make sure that our meshes are always watertight. Let's look at the other problem that we might run into whenever we working with geometries and getting it ready for simulations, which is scale. Okay, so I'm creating the good old box using a match size node to put it flush to the ground. I'm using a node called rest, and if I click tab on my keyboard, type in REST, there's a node called rest position. And this is the node I used to show you this example. Okay, so what does rest node does? Well, what rest node does is it kind of remembers the position of this geometry and it stores in memory. And whenever we do another transformations like rotating, scaling, or whatever you want to do with this mesh, later down the network, we can get back to this state. And I'm going to show you how it's done here. So I'm using a transform node to deliberately scale my object bigger than normal. Okay, here it is. And I actually initiate the geometry Tommy to see that indeed we are completely humongously out of bounds where we shouldn't even be. So I put down Tommy just to show you the reference how big this geometry is and that we have a problem, right? I started with this box here, okay? I used the match size node to make it flush to the ground. And I mean, the scale now looks all right, okay? So this is a good scale. But if I import the object and it's like this, and if you zoom out, it might look, oh, this looks okay. I don't even have a problem, looks like. But as soon as you put down Tommy, which is physically accurate, around 2+ meters, like human scale figure, we know that we have a huge problem. Our geometry is like 100 times bigger than it should be. And it's of paramount importance to have a scale for objects that are true to real world size. Let me illustrate. What if you want to create a destruction of a wall? Well, you import your wall, it is 10,000 times bigger than it should be, and if you're taking that geometry, feeding it into the RBD bullet solver, and solver has to solve this, but it works on accurate data, and your data point, which is scale, is not accurate, so you're going to run into a whole bunch of issues. The simulation is not going to be accurate, there's going to be problems with your constraints, there's going to be problems with a bunch of forces, and there's going to be all kinds of weird and nasty things that can break your simulation. So we need to make sure that our position, or should I say scale, is true to real world scales. So let me show you how I did this. So I used a rest node to store the original position of this node. Then I deliberately scaled it, and I used a wrangle node to get my position back to where it was. So that's basically the workflow, very simple. The rest node comes at the top, and then a wrangle node at the bottom, where I say, give me back my position. Okay, so that's about scale. Let's talk about thickness for a moment. Okay, I'm going to zoom in a little bit. I'm creating a box. Again, making it flush to the ground. I'm deleting a primitive to illustrate the problem. You see, there is no thickness for my geometry. And this is not something we can work in simulations. For simulation to be realistic or semi-realistic or believable, there has to be some kind of thickness in the walls, okay? We can't feed this into this bullet solver and expect for it to return believable results, because each and every geometry in real life has some kind of form, right? Even paper, it has some form, but it's very, very tiny. So we need to add thickness. And we can do that with a simple poly extrude node to give our geometry some thickness. We press tab on our keyboard, type in extrude, and there's different kinds of extrudes you can actually choose from. There's extrude old, extrude volume, and poly extrude. And I chose poly extrude node. I picked my geometry, put my display phone on the poly extrude node, press P on my keyboard, and with the distance slider, I can add whatever thickness I want, okay? Very simple. I think this is self-explanatory, and we can move to the next example, which is intersections. Okay, I'm creating a rectangular box. I'm using a match size node to make my object flush to the ground. Then I'm using a node that's going to copy and transform my box. And it's done by this node, copy and transform, right here. And it does what it says. It copies the original geometry, and it's going to transform in any direction you set it. Okay, I'm gonna select this node, press P on my keyboard, And you can see this as I talk you through this. Right now it's set to 2.3, just to illustrate that there can't be any intersections when we do RBD simulation. Unfortunately, we can't do this. The geometry must sit flush to the other geometry. There can't be any intersections, okay? It has to be flush, like this. Okay, and how I do this? How can I solve this? Well, we know there's a match size node, right? So I'm gonna put display flag on this merge node, and voila, we have solved this problem. So I'm gonna walk you through how I did this. So I created a box, used the match size node to make it flush to the ground. Then I copied the same box that you can see right here. I used the same match size node to match it. And then I used another match size node to reference the position of the previous box, and the end result is this. Very simple. And if you want to kind of copy the settings, well, the first match size node is set to justify min to the same, and the second one is set to min and to the max. So that's how we figure out the intersections, and that they always are flush to each other and nothing intersects. Okay, that was base geometry preparation. I mean, there's a lot of things that we have to make sure that we kind of put in place these techniques before we even think about pulling our geometry into the sim. Okay, we started with position and orientation, then we moved to the normals and making sure that our geometry is shaded correctly, then into grounding so that our geometry is flush to the ground. Next we looked at water tightness, so that there can't be any holes in our meshes. It has to be one solid piece. Next we looked at scale, that our objects need to be always true to real life scales. It can't be shot up by a factor of 1,000 or by 100. It has to be grounded in a real world units. Next, we looked at thickness, because our geometry can't have only one single polygon, like this, like paper. We somehow need to add thickness, and that is done by polyextrude node, or you can manually go and make your own custom models or get them from our marketplaces, or or maybe your art department gives you. So you might make sure that that is in place. Next was intersections, or geometry can't intersect with each other. We always need to make sure that it is like this, flush with each other, and if I see through it, nothing overlaps. So vital. Okay, I think we're ready to move into the step number 2 of my destruction workflow, which is fracturing. How do we create these pieces? Well, let's talk about this. I'm gonna select this node and I'm gonna jump right in. I'm gonna toggle off point numbers and points so we can look at this geometry more cleanly. And I'm gonna let you have a read about what fracturing actually means. So you can take a second to read it. Okay, let's look at the first example. And the first example I want to show you is Voronoi fracture with an ISO offset node. Let me walk you through. I'm creating a box, as always, using a match size node to make it flush to the ground. Then I'm converting this geometry into a volume. How did I do this? Well, if you follow along, press tab on your keyboard, type in ISO offset, and there you go. You have an ISO offset node. If I click it and let go, what I can do is I'm gonna actually use my own node because it's already commented out. I'll take my geometry, which is this. I'm going to plug this into the source. I'm going to put display flag on this node. And you see it sort of looks like this, well, volume. It sort of has this fog characteristics. And if I press P on my keyboard, get those node settings up for the ISO offset node, and we can see there's an output type setting. We can choose from ISO surface, we can choose SDF volumes or tetramesh, but in this example we're interested into the fog volume because we're going to use this volume to scatter points inside of it. Okay, I'm going to scatter some points in it using a scatter node. I'm gonna choose 70 points for this example, and right after this I'm going to use a Voronoi fracture node. I'm gonna put display flag to it, and you see what happens is Houdini is referencing back to these points we just created and is running a Voronoi fracture basically a method to fracture geometry based on these points. And if I put my display flag on this node and actually on this, and I'm gonna reference this and initiate my drawing, we can see what is happening. Inside of every Voronoi cell there is a point. I hope you can see this, but if you don't, I'm drawing them in for you. Okay, each and every cell has a point. Well, how did it happen? Well, we created it using the combination of ISO offset and the scatter node, right? And this is what's called Voronoi fracturing. It's using points to fracture our geometry. And to further show you how this works is we can use how many points we want. We can set 1 point, and the mesh is going to be basically the same as it was before. If we use 2 points, we're going to have 1 fracture. If we have 3, there's going to be 3. And as I move the slider, my geometry keeps on getting fractured until I say, you know this, I like this result, please stop. And this is how we can create it. We create our geometry, make it flush to the ground, then we turn this into a volume which allows the points to be scattered inside this and then fed into the Voronoi fracture for us to get this cool fractured look, which is pretty neat. All right, that's about Voronoi fracture with an ISO offset node. Well, would there be cool if there would be other techniques or other nodes we could use to do the same thing? Well, there is, and it's called VDB from polygons. We follow the same procedure we did just a moment ago. We create our box, make it flush to the ground, and instead of using the ISO offset node here, we're plugging in VDB from polygons, and we're essentially having the same effect. Okay, we're choosing excuse me. Let's select this, and we can change the voxel size. Okay, until we have something that resembles this cool fog. And when we're happy with the result, we follow the same steps. We add down a scattered node. We scatter as many points as we want to see in our fracture, 130 or 121, and we fracture our geometry based on my points using Voronoi fracture node. And we have a similar result, just using a different node this time. All right, quite easy, I would say. Well, let's look at Voronoi fracture by using Voronoi fracture points node and scattered node in combination. Let's see what it's all about. Well, I'm going to create my box. I'm going to use a match size node to get it flush to the ground. Then what I will do is use a VDB from polygons to convert my geometry into this volume. I'm going to scatter some points in it. And then I'm going to use called Voronoi fracture points. And what it's going to do is it's going to give me, actually I'm going to put display flag here, it's going to give me a whole bunch of points clustered in these impact points. See? Well, and if I put my settings for the node, we can actually specify how many points per area we want to see. The lower we go, the less points we're gonna generate. Okay? We can generate surface points, we can generate interior points, we can generate even exterior points. And then we basically merge everything together. My scattered points that come from this box, that I have scattered points inside of it, and then we merge it together with Voronoi points, and the end result is this. And right now it doesn't look like much, but if I go into the Voronoi per points node and change the settings a little bit, I can make it look a little bit more interesting. Let's play around with the settings. Okay. See? Okay, so that is Voronoi fracture with Voronoi fracture points plus scatter node. Now let's look at the next example, which is Boolean fracture. I'm gonna put a display flag on my geometry, and let's talk about what Boolean actually means. And if you come from other softwares, we know that Booleans are actually geometries that cut away from each other. And to give you a better illustration of this, let me put a reference flag on copy to points node. And we can see that, sure enough, in the middle we have our very complicated 3D box. And what we're doing is we're taking a bunch of oriented grids and cutting our wall with them. Now, how do we do it? Well, first we create a grid node, just a random square grid with a few rows and columns. In my case, I have added 50 on each, so it's divided evenly. Then I add a mountain noise to add irregularities in my geometry. And this is going to come in handy because all of these spikes that you see here is going to add the interior detail on each and every cut. We're going to see that in a second. Okay, but for it to work, I need to generate an orient attribute, and I can do that with the attribute randomize node. Okay, in an attribute name, I specify orient, and when I use copy to points node, cleverly enough, it's going to understand how to take those grids and orient them in random directions. And this is very important for us because now we can use this geometry to cut into our wall. So we take our wall, right? We have this plain wall, doesn't look anything right now, but if we cut into it using these 3D uneven planes that have been generated using this technique by creating a grid, adding a simple noise, and copying this grid based on orient attribute. If you read the network, take a screenshot, maybe you can try this at home. Then we pipe this into a Boolean fracture node, and voila, we have a Boolean fracture method. And oftentimes, Boolean fracture method is often preferred fracturing method because it is you can better control how it looks. It gives much more believable look, and is just going. It's basically now an industry standard at this stage. So Boolean fracture, definitely experiment with it. But I think it's self-explanatory, and we can dive into the next one, which is RBD material fracture. And let's see what this is all about. Well, I'm going to create my rectangular box, which we have seen already 100 times. We put it flush to the ground. And then I'm adding down a node called RBD material fracture. And if you're wondering to yourself how you can access it, you're typing in RBD material, and here it is. Okay, it is right here. So you pick that, you pipe in your geometry in the first slot that says geometry. And what's going to happen, if I may click P on my keyboard and open up the settings for the RBD material fracture, this node is going to fracture my geometry based on a material type. And you can think of this node as a all-in-one node that does multiple things all at once. It basically cuts with the booleans, it adds chippings, and adds all kinds of details and constraints. So let's look. Okay, so in the primary fracture tab, I have two tabs. And what this node is doing is it's adding two fracture levels. So we have a level number 1, which has scatter 5 points, okay? And then on top of that, it's add another second level, okay? And that's why you see this complicated look. And on top of that, what we can do, if I open up this example here, and this is the result of RBD material fracture node. We're having chipping. If I toggle it on and off, I'll give it time. We can do edge detail. See how all of these things affect the end result for geometry. And we can play around with noise heights. If we want it lower than that, it's going to create a lower detail. If we want to up it up a little bit, we have like very experimental look that we may or may not want. Probably don't. So we reel it back something that looks more realistic like this. And this node does multiple things at once. Again, think of it as a preset node that you can quickly get believable result. Okay, so that is RBD material fracture based on concrete. And you can set the material type at the top. I forgot to tell you. Okay, let's look at the RBD material fracture once more. And what is different in this one is, let me check. Oh, okay. This is supposed to be wood. Let me rename this on the fly. Not woody, but wood. Okay, RBD material fracture material type wood. Let's take a look. I'm creating a simple box geometry using a cube node. And hang on. I'm adding in these settings for it to kind of resemble a little bit of a plank. Then I'm using mesh size node to get it flush with the ground. Again, as we learned just a moment ago, I'm using an RBD material fracture preset node, and I'm choosing from the menu up at the top material type. Instead of concrete, this time around I chose wood. And if I click Shift W on my keyboard to see the edges of it, I can see this cool pattern that's been created for me. You see this? Whoa! This is how real wood actually sheds itself. And if I open up, put my display flag on the exploded view node, I think this is going to illustrate this a lot better. See, this is how real wood behaves. We have chipping a little bit sort of like vertically, and we have those sort of shard looking pieces. And that's what material fracture node can give you, this sort of how a real wood would behave. Super simple, play around. There's 1,000 settings you can use to create an effect that you desire. Next, I want to do the same thing but for a different material, and this time around is going to be glass. I'm going to put this flag on the box node, And this time I created this square that is going to resemble a glass. I'm going to flush it to the ground and use the same RBD material fracture node, but as you may guessed, this time, instead of using concrete or wood, I'm going to choose the material type glass. And when I do so, and add the settings that I like, I can create these very cool shard looking fractures. And if I use my exploded view, that's that. So that's an RBD material fractal glass node that's going to give you a believable glass sharing results. But we can take it up a notch and use an RBD material fracture with the points that we specify, or you can think about them as custom points. We can use this preset node in conjunction with our custom points to create fractures that look a little bit more customized and not as preset-y looky. So let's look at how that's done. Well, I'm going to create a rectangular box, flush it to the ground. I'm going to use a scatter noise to scatter a few of the points inside to create my custom points, okay? And then I'm going to use a merge node that's going to merge the results which just look like a few steps back. I'm using VDB from polygons to generate a volume, and I'm scattering more points into that, and I'm going to use a Voronoi fracture points to generate impact fracture points. And then what I want to do is I want to marry these yellow points together with the scatter points, right? And the end result is this. And at this step, what I can do is I can pipe this into the fourth slot of the material fracture node. And when I do that, what I can do is tell this RBD material fracture node, please fracture my geometry based on my own points. Okay, to give you a better illustration of that, I'm going to select this RBD material fracture node, press P on my keyboard. I'm going to head over to the primary fracture tab, and to make sure this node uses my own points, what I can do is scatter from attribute instead of clicking volume. That's going to basically use all kinds of parallel noise, alligator noise, simplex noise, the stuff we just saw. I can specify for it to use my own attribute, which is my points, okay? Input points here. Actually, I'm going to put display flag here, and when I click here, there you go. I have my own input points that this node is using to fracture my geometry. Okay, so this wraps up the step number 2, which is fracturing, and I think we can jump right into the clustering. Okay, so this is the third step into the chain. We now know how to prep our geometry, we know how to fracture it, which is already huge. Next thing we need to do is cluster. And what is clustering? Well, at the beginning of a video we went over it, but if you wish to read, this is what clustering is all about. We're clustering or grouping or fractured pieces together so they can act as a large unit during a simulation. And there you can see it on the screen, right? Instead of those even fracturing pieces we had in the previous step, now we are generating these blocks that look, well, if you ask me, they look quite realistic. See, this is joined together with this one. Okay, here we have a block here, and this makes up for much realistic destructions, because in real life when stuff breaks, often than not, you're gonna have pieces like this, unless it's something like glass, but even glass has clusters. But how we can do this? Well, let's look at a few techniques, and these techniques are going to be here. So, as always, I'm starting with the box. Then I'm going to use a transform node to give my box a Y direction. So then I can use an RBD material fracture to fracture it. Then I'm going to use a node called RBD cluster node that's going to automatically fracture my pieces into random chance, basically. And then I'm going to throw down an RBD bullet solver and pipe this into the first input. And when I do so and play back my animation, we can see that. Now let me stop this. Find a moment for this to okay. You see how realistically this breaks? Instead of having random small pieces flying everywhere, we're having really cool pieces that look way more realistic than if they weren't clustered. And this is mainly thanks to RBD cluster node right here. And if I use Q on my keyboard and drag on the RBD cluster node, what I can do is tell Houdini, please bypass this node, give me a result that doesn't include this node. And see the result? How boring it is. Everything's basically destroys in smithereens. Not realistic, maybe glass would break that, sure, but not a concrete, not a concrete. So we use RBD cluster node to give this a much more appealing and more realistic look. Very simple. And I think we can look at another example, which is Voronoi clustering technique. So shall we take a look? Let's go. Let's create a box, then use a match size node to pull it up on a grid. Then I'm going to use something we already saw, ISO offset node, that's going to convert my geometry into a volume, which is like a fog. Then I'm going to scatter some of the points inside of this volume using scatter node. And then I'm going to use cluster points node, which is going to cluster my points based on their position. And you can find this node by tapping tab on your keyboard, typing in cluster points. You throw that down, and you pipe that your scattered points into the first input. And if I press P on my keyboard, you can, with this node, adjust how many clusters you want. 1, 2, 3, 4, 5, 6, 7. And if I actually show you the end result and do this live, you can see that with this node, I'm telling Houdini, well, maybe I want just 5 pieces instead of 10, Maybe I want 5 pieces that stick together. Then, it's basic as this, basically. I use cluster to points node to make clusters. Then I fracture the geometry based on my points. And then cluster everything together. Super simple. Alright, let's look at RBD material wood clustering. How we can cluster wood. And to do that, I'm going to use a tube node with these settings. Then I'm going to use an RBD material fracture node to fracture this geometry based on the material type. And you may already guessed, I'm going to use a material type called wood. And that's going to give me this very wood-like fracture vertically. And then what I'm going to do is I'm going to add an assemble node. And what this node does, it's actually very interesting. It's going to create packed primitives for me. And to explain what packed primitives are, we need to click Control, middle mouse on the material fracture node. And when we do that, we can see that this geometry or wood piece has an enormous amount of points, primitives, vertices, and polygons. The numbers are outrageous. What if there was a way to reduce this so it's easier for our computer to compute everything? Well, there is, and that's what the assemble node actually helps. And it does 2 or more things, but mostly it's used to, number 1, create a name attribute. So our bullet solver understands each piece as an individual or unique. And second, we can create a packed primitive, which basically let me zoom in, which turns which gives a point per piece. So basically we're reducing the number from let me actually maybe compare this like this. I'm gonna tab click on that one, I'm gonna pin it, and I'm gonna control click on assemble node. Actually, hang on. I'm going to control middle click on RBD material fracture, and I'm going to pin this. And I'm going to do the same for an assemble node, and I'm going to pin it so they're both can be seen, and actually make sure I'm not on top of those. And what we can see is that assemble node reduces the number of points, primitives, and vertices by a magnitude of what? 10? No, 100? If you know math, let me know in the comments. So basically, overall, it reduces the number of points we have to deal with, which is great for our system. And I'm going to put that into a bullet solver to run my dynamic bullet simulation. And we can see what it returns for us. I'm going to click play. And let's give a time for Houdini to think and show us the end result. And there you go. I may want to zoom in a little bit so you can see what is happening on our screen. It's lagging a little bit right now because I am recording as well, so that takes a hit on my computer. But the blue marquee line at the bottom of our screen, it's actually taking this simulation and is putting it into the RAM. So up until this point, everything has been recorded into our RAM, and on the second play, everything should be faster. Yes, everything has been stored in my RAM right now, and I can see the simulation in real time. If I click this little icon, that's basically a real-time toggle. And there you go. We have created a wood simulation like that. Alright, next, RBD Paint organic clustering and bigger chunk clustering. Originally, I wanted to show you these two examples as well, but during this recording, I had made a mistake, and I'm not gonna, unfortunately, be able to do this. So we're gonna put X's on this. I'm gonna take it blame, and in the next video, I'll make sure I don't repeat the same mistake. But how about we go into the step number 4 in my workflow. And step number 4 is constraints. So let's talk about them. Step 4, constraints, and there's a bunch of examples that I want to show you here. And let's read what the constraints are. In RBD, rigid body dynamics simulations, constraints are rules that hold pieces of fractured geometry together until a certain force breaks them. They are essentially for controlling how and when your fractured pieces separate during a simulation. And so this right here is basically a constraint network. And what constraint network is just 2 points in space that are connected by a primitive, and that's all there is. And these constraints have a rule how these pieces should behave and what kind of relationship they have. Are they elastic? Are they rigid as one piece and they never break? Or are they sort of like a Lego that you glue them together and there's enough force that's going to break them apart? And we'll actually look at this in a second, and it's going to all make sense. But that's what constraints are. Okay, so let's look at first constraint type, which is glue constraints. And to give you an illustration, let's create a box on our viewport. Let's move it up in Y. And let's put down an RBD material fracture node. And let's fracture it with the concrete preset. And if I want to basically visualize my constraints, what I can do is look at this like pinkish pin that says constraint geometry. And when I actually, let me disconnect this here, I'm going to type in null I'm gonna throw it in my network. And when I take this little thingy and put my display flag on it, I can view and illustrate my constraint network that's coming out from RBD material fracture node. Well, how it appeared in the first place? Well, if I go into my RBD material fracture node under constraints, there you can see we have enabled constraints and generated them. And this is what I talked just previously. This RBD material fracture node is an all-in-one preset node. Not only does it fracture our geometry, add chips and edge details, but it also adds constraints. Okay, well, what happens if we run our bulk dynamic simulation with the glue constraints? Well, first of all, RBD material fracture node adds glue constraints. You see there's a name glue. And what glue constraints are is very simple. And I'm going to go into the first, on our first keyframe. We have a bunch of fractured pieces here, okay? There's a piece, there's a piece, there's 100 different pieces, right? You see them on the screen. And what glue constraint does is you can imagine a real life glue that has the compounds and formulation that glues them together until a force has been met that breaks or shatters this glue apart into the smithereens. So think about glue as a funny as it sounds, a real glue. When you add enough force, it's going to break. And if we run the simulation real quick, see? We take our geometry, like we take it up in the Y, and then say to the solver, drop it down, and use the strength force to break them apart. And actually you can find the strength parameter actually in the RBD material fracture node under, RBD solver actually. And if I go through the tabs, collision, forces, well, for one we have a gravity, but then if I try to find where it was, hang on a second, okay, here we have, there's a glue constraint that we have set, and there's a strength parameter. And if I kind of, for fun, make this a huge number, theoretically we shouldn't see this wall break. Yep. So the glue constraint is controlled by the strength parameter, which basically says if this force strength exceeds, break these glue constraints. And that's what the strength parameter is all about. So if we dial it back to 100, run our simulation, we can see them break better. And alternatively, if I put it to 50, it should, in theory, break apart more easily. So this is all fun and games. We test different values, we see what sticks. There is no really one rule that says glue constraints should be 50 or glue constraints should be 1,000. It's all about testing, experimenting, getting real-time feedback, and from that, readjusting our parameters and sliders. So it's all playing around, messing around with the parameters. It all works like that basically in Houdini. Okay, so that's what glue constraints are. Another type of constraints we have is soft constraints. And the way you can think about soft constraints, I showed you this thing with my hands, which means elasticity. Soft constraints make geometry sort of elastic. Basically have this jelly effect. They're more like that, So that's what's, and I'm better off showing you the result. So I'm gonna run the simulation. See how these constraints kind of have more elasticity, and the breakage doesn't happen as quickly. It sort of takes its time. It kind of thinks, oh, well, what this piece is doing, what that piece is doing, and so that's what the soft constraints are. So I'm creating a box, adding it up on the Y, so it has kind of like a space to come down. Then I'm getting a material fracture node, which generates these soft constraints. If I can find them. Where are they? Actually, hang on. Oops. Okay, so here they are. They're in RBD bullet solver. And I don't think my RBD material fracture generates them. Hang on. We have constraints. Oh, they do. So we have a glue constraint name here, which are soft. And then we pipe everything into the RBD bullet solver. And we're also specifying that these are soft constraints. And when we do, we have our simulation ready. So that's what soft constraints are all about. Next, let's look at hard constraints, shall we? And what hard constraints are? Well, I'm creating a box, putting up in a Y, so the box kind of has a movement and kind of breaks. I'm adding RBD material, fracture node, and I'm generating hard constraints this time. P on my keyboard. See, glue constraint name is hard this time around. And if I'm going to put the display flag on them, here are my constraints that help me visualize this node. And I pipe that into the RBD bullet solver, which as well has the glue constraint name set. And we can see what hard constraints are all about. Let me zoom in a little bit more so you can see. See, it's a one rigid piece. That's what hard constraints are. The pieces do not come apart. It's all one rigid whole piece. Boring, I know, but that's what hard constraints are, and they come in handy at times when you need them. So that's in your toolbox. We have talked about glue constraints, we have talked about soft constraints, we have went over the hard constraints. What if there was a way to merge and combine constraints? Well, there is. And let's look at an example which is about soft constraints and glue constraints together. So I'm going to have up my box. I'm going to transform it, give it a little bit of rotation to kind of better visualize what I'm about to show. I'm going to fracture the geometry. I'm going to add a few points there. Actually, I'm going to turn this off. And if I'm going to visualize my constraint network, here it is. And if I press play, actually I can see this network as well. And if I actually go into the RBD, oh no, I can't. Anyways, so I fracture my geometry. These are the constraints. I pipe this into the RBD bullet solver. And what I can do in the solver is a neat little technique. And it's under the constraints tab here. I type in soft and glue, and I'm going to add an angle threshold, which means when we exceed this angle threshold, I want other constraints to kick in, and that's done by switch to constraints, this mode. So when I do that, look at what happens. And actually I'm going to go into the visualization, and I'm going to click not show geometry, but I'm going to make a color white. I'm going to turn this into flat shaded. And we're going to look at this example. And I'm going to zoom in a little bit from the other one. Do you see how elastic this box falls to the ground? It doesn't come apart rigidly, you know, it's not a whole piece. It's not a soft constraint all alone. It's not a hard constraint. These kind of merge together. So we have this elasticity, and when it kind of reaches a threshold, hard constraints kick in and it kind of breaks apart. And that's how we can merge constraints. Or a more technical way to say that would be we are switching from one constraint type to another constraint type by creating two constraints on the same geometry and piping them into the RBD bullet solver and adding a rule when hard constraint, when a soft constraint should switch to a hard constraint, and the end result is this, and it's much more realistic than if you would go only like glue constraint way. So this is probably my favorite way nowadays to create destruction effects. So that was it for the step number 4. I think we can move on to the step number 5, which is impulses and triggers. So what is that all about? Well, there's a bunch of examples for you, but in RBD bullet dynamics simulations, constraints, constraints, hang on, we are into the impulses. There we go. In RBD rigid body dynamics simulations, impulses and triggers are what makes your fractured objects start moving, break, or explode. They are the push that interacts without constraints and RBD pieces. So that's what impulses and triggers are, and we need them because we need this interplay between something makes some sort of like cause and effect. Something causes this explosion, right? That's how it happens usually. Something is triggering this thing to break. So let's look at this real quick. And the one way how you can create a trigger is by using a velocity using a wrangle node. And if I create my box, put it flush to the ground, fractured using RBD material, fracture node, here it is, then I'm adding a wrangle node that sets the initial velocity of points to 7 units a second along x-axis. So let me demonstrate this. So actually, hang on. For a better demonstration, I'm going to select this node, press P on my keyboard to put up the code that I have written, which is a VEX code. And what this VEX code basically says, v at velocity equals, please set it to x-axis, which is going to be x-axis in 7 units, 0 in the y, and 0 in the z. So essentially, what we're saying with this code, based on, and we're saying run over points, right? We're saying please add a force in this direction 7 units a second with a single line of code. And this is very easy to remember. Okay, v at v equals set 700. Or you can use any other number. The higher the number, the higher the velocity is going to be. So let me visualize this, because I think that's going to be a much better way to learn. So we're gonna, let's see. So why are we seeing this? And I found a problem. I accidentally put R in this. So that gave me an error and the whole simulation broke. So when I fixed that, no longer we have any errors. So I have my solver selected, and if I play it, we can see that we have added a movement to our simulation just by using an attribute wrangle node. Very simple, straightforward. How about we look at another example? Sorry. Essentially, what I'm doing next is taking everything that I've done before, except instead of using attribute wrangle node, I'm going to use a node called point velocity. And this node sets the initial velocity of your points to 7 units per second along x. So basically the same thing as an attribute wrangle. But instead of writing this code with our hands, or remembering it, or copying it from somewhere, what we can do is we can lay down a point velocity node. So I press tab on my keyboard, I type in point velocity, and here it is, this node right here called point velocity. If I take this node, drop it in my graph, press P on my keyboard, there's a little tab that says add velocity. You see it? Here it is. And there's a little check mark next to it. So I want to enable this. Okay. When I enable it, there's a vector that appears. So basically what we can do is we can add a velocity in x direction, which is sort of like our way, in y direction, which is shooting upwards, or in z direction, which is that way. Okay, so we know that to replicate the previous effect that I showed you with the attribute wrangle node, we can use this point velocity node, but we need to add the same velocity 7 in x direction. And sure enough, if I watch the result, we have completely, absolutely the same effect because we just did the same thing. Okay, very simple. You can use these two nodes to add an impulse or trigger just like that. Super quick, super simple. But what if we want to add our own collision effect, such as this ball right here? It's basically the example we looked at previously. So we have this little blue ball that goes through the wall and makes a hole in it physically, without using any codes or anything like that. Basically, maybe you have a geometry or maybe you have an idea in your mind how you want this effect to play out. So maybe it's a bullet, maybe it's something, I don't know. But what I have done is I created the box. I used a match size node to make it flush to the ground, used an RBD material fracture node. What I did next is I generated the constraints using RBD constraint properties node. And what this node does, it tells the RBD solver how each constraint should behave. And if I actually put down a null, and if I look at this, see, it creates the same network we looked at the previous step, which is step number 4. So we have these constraints, we have this relationship between our pieces, and it's done with this custom constraint properties node. So I add that in, and I specify that I want glue constraints and I want soft constraints. And what else I did? Okay, I enabled switch constraints to enabled. Sometimes it's disabled. I put it enabled, and I want to go from glue constraints to the soft constraints. Okay. Next, I put down an RPD configure node, which is going to tag my geometry with bounds. And here I have the, basically, how do I explain this to you? Okay, maybe like this. So I have my geometry, but if I don't have these bars on each of these sides, my geometry is going to basically shoot in that direction, like immediately. There's not going to be anything that holds it in place. So if I visualize this, there's an input, the fourth input, which is exactly for that, which is for the bounds. Okay, and I have created these bounds right here. I used the box, I used match size node, and I transformed them, duplicated them, and I create sort of this basically bounce or stick that's going to make my wall be in place. And that's done by RBD configure node. I pipe this into the fourth input, and I make sure that I enable this check mark, and I set my active to 0 and use the bounce check mark there. And what I'm telling Houdini is basically use bounce to deactivate these regions. Okay, these are no longer active, and the only active place is going to be here. Okay, that's what I'm essentially doing with this setup. It's very, very simple. I'm using a bound geometry, and I'm piping that into RBD configure node to mark these bounds, so that the bullet solver can understand which parts of my sim are breakable and which are not. Okay, And what else I'm doing here? Well, I am using a sphere, which is basic sphere, and I'm using a transform node to animate it. See, if I open it up, I can scrub my timeline and see that this ball has been animated with simple keyframes. And what I do then is I take the output of that pin and I plug it into the RBD bullet solver collision geometry input, which is 1, 2, 3, 4th from the left. Okay. From there, what I have to do is I have to go into the RBD bullet solver, collision tab, and collision type change from static animated to the deforming. And when I do that, my simulation is here. So that's a fantastic way to add these impulses and triggers and our collision geometries to our sims. Self-explanatory, super easy to set up, and if I show you these setups, you can try them at home, and everything has been commented out, so it's easier for you to learn and try to replicate this on your own. I think now what we can do is we can look at step number 6, which is simming. In RBD, rigid body dynamic simulations, simming refers to running the physics simulations over time. It is the process of calculating how your RBD pieces move, interact, collide, and respond to forces. And we're looking at this setup that we looked at previously, and basically all of our work that happened upstream, okay, or geometry that we created, or geometry, or constraints, okay, or rules, then our bounds, everything gets piped into our little brain. I hope you can see this, but we're using an RBD bullet solver, which is going to be the central brain that is going to look at our geometry, our constraints, our bounds, our rules, and even our collision geometry or collision. Everything is going to come together, and RBD bullet solver is going to make a calculation to spit out us a result. And so that's what simming actually means. We're just using the RBD bullet solver to run a dynamic bullet simulation. And there's only a handful of settings that I, at least on my current experience, use. And namely, it is the collision tab, where I specify either the geometry is deforming or it's animated. So that's probably the setting number 1 that I use, is this collision type. Okay. Then the next one is probably, so the first one is this setting. Okay, so this is number 1. Next one is ground collision, which I always set to ground plane, so that we have a ground where our forces can interact with. So we can use none, and our simulation is basically not going to work. See, if pieces basically go through into nowhereness, basically. So I use ground plane. That's number 1 that I do. And usually when I put the ground plane down, you see it's shaded. I can't really see what's after it. So usually the next thing that I do is I go into this visualization tab right here. And when I go there, so maybe I don't want to visualize these grounds as shaded. Maybe I want to see it as a wireframe. Well, I have an option to do that. Well, what if I want to put it back to the shaded, but instead of changing that parameter, what if I want to see just the collision shapes? Well, if I zoom in, there they are. Basically, what is happening is RBD bullet solver is not simulating all our geometry. What is happening is the solver is taking, you see those blue pieces? it's simulating those pieces instead of actual geometry, and that is called the collision shape. So we can visualize that and see how that works. But we can also simulate, not simulate, but visualize or active objects. So if I play my simulation once more, okay, these pieces that are in green are active. Well, what if I want to visualize the sleeping pieces that kind of settle down as the time goes and progresses? Well, I can do that as well. And if I give it enough time, they should or should not turn, well, they kind of go to the red zone, but they get to the yellow. So I'm going to untick those. Ground, we talked about that. Constraint geometry, we can visualize that as well. There it is, the white, these white lines. There it is. Constraint geometry, we can visualize that as well and troubleshoot for some reason. So that's basically in the visualization tab. Forces, you can enable or disable gravity. So if I disable gravity, you know, the simulation looks kind of broken, because in the real world, oftentimes we do have gravity, right? Unless we're in cosmos. So that's gravity. Always put it on and it's minus 9.8. So I use that. Then the constraint tab, which I always use to set my constraints. In this example, they're set to soft and glue, and there's a rule in place for the distance. If this unit is being broken, then I want the constraint to switch from soft to the glue. What else do we have here? Well, we have a time scale. What if, for some reason, I want to slow down or speed up my simulation? Well, I can do this with this slider. Let's halve this and replay, and everything is half slower than it was previously. Well, what if I want to speed this up to 2 times? Well, I put it 2, and actually the simulation breaks because the ball goes through so fast that the calculation can't take place. Which brings us to a pretty cool property, which is a substep. Basically, what substeps are, you can think of them as a resolution. So the higher the number, the longer it's going to take to sim, but you're going to have more quality results. But oftentimes, what these substeps do, they sort of amplify all of the settings that you have put in. So the constraints could get stronger, and the fracture may not look as it did before. So I'm going to put 10, and I'm going to see the fracture. See, the fracture seems to be stronger, right? So that's what the global substeps actually is. So when you change this number, usually you want to readjust the settings of the RBD bullet solver or your constraints or the network and your work upstream. What else? So we talked about setup. We talked about global substeps. This we can skip. Oh, one overlooked thing is when you go in any tab, really, there is this reset simulation and start frame setting. Basically, when you change a setting either upstream or in this RBD bullet solver node, usually a good practice is either you click the reset button, which is going to reset your settings and kind of give you a fresh output of your work. Or alternatively, what I do is I click on this little checkbox that says first frame in the animation tab there. So let's say I'm on the 96th frame, I click here, and that's basically the same as resetting the simulation. And I'm going to have a fresh result there as well. So it's up to you whether you use our reset simulation or you go here and click on the first frame. That's up to you. But when you want to click reset simulation is when RBD bullet solver kind of throws kind of a weird result, something you're not expecting. Maybe you don't see the ground plane, maybe you're not seeing collisions, or any other reason. So it's a good practice to reset the simulation and starting fresh. Okay, what else? We have guides, visualization, time, and output. So that's for the step 6. I think what we need to move forward next is step number 7, which is caching. And if I put my display flag to this container, we have the same geometry that we talked about just a moment ago. And I'm going to change the color of these node boxes. Actually, if you're wondering how these boxes are created, there's this little toggle button there up at the top. If I open it up, there's these sticky notes. And when you click there, you basically have a sticky note, and you can change the color by pressing C on your keyboard while your mouse is hovering over the network view, and you can change to whatever color you want. And these right here, if you're wondering, is this, which is a network box. So you select, for example, these nodes, click Shift O, and that's going to give you a network box over the bounds, which are, the bounds. If I put a display flag here, those are the bounds we talked about. And so let's talk about caching a little bit. I think we need to go back. We kind of deviated a little bit here, but in RBD simulations, caching refers to the process of saving the results of a simulation to disk, so you don't have to recompute it every time you play it back. It's a crucial step in simulation workflows because physics simulations can be heavy and slow to calculate in real time, and that is of paramount importance to offload the work from your CPU and RAM onto the SSD disk, so you can play it back faster, without lag, without delay, and without skipping frames. How we do that? Well, we take all of our work that we have done upstream, okay? We take everything, our geometry, our fractures, we take our constraints, we take our bounds, okay? We take our collision geometry here, and we use couple nodes to basically cache the results of everything that comes out of RBD bullet solver node, and we plug this into this sort of setup that I'm going to guide you through. So there's multiple things that come out of RBD bullet solver node. We have our geometry, then we have our constraint network, then we have our proxy geometry, which is basically a simplified version of our mesh. Okay, and if I go into some other, see? So proxy geometry is basically a simpler version of your simulation. That's what proxy basically is. It's simplified geometry. So we take all of that, our constraints, and our proxy geometry, and what we do next is we use transform pieces. And actually, we just transform the pieces that are low res. We just need points. So we drop down a transform pieces node, like so. We take the second input, which is the template points. We put it into the proxy geometry, and we take the first input of the same node, geometry to transform, and we're transforming geometry, which is high resolution geometry. See, if I actually put down a null, actually we're not going to see this. If I try to visualize this, we're going to see that out of this output we have high resolution geometry. So what we want to do in this step is we want to take proxy level points that come out of proxy level geometry, and we want to map that onto the high resolution geometry that comes out of RBD configure node. So we're essentially mapping points to our higher resolution geometry using transformed pieces node. See? There's no real settings here to worthwhile mentioning at the moment. So you take the first input, use the high-res geometry. Second input, you use the proxy geometry. And what you do then is you pack all of these streams, your proxy geometry, your constraints, and the transform pieces nodes into an RBD pack node. Basically, you pipe everything into an RBD pack node. Then you use the same node to unpack everything, and then you pipe everything into an RBD IO node. And if I press P on my keyboard, this is where you export your simulation onto your disk. So you offload the work from your CPU and your RAM and onto your disk drive. So you choose your base name, base folder, when should it start, when should it end, and you say export or save to disk. And then what you can do is use the same node. You can copy it like this, cut all of the incoming those lines, and you click load from disk, and there you have it. Now your simulation is exported just like that. Now we don't see the ball because I quickly want to demonstrate that for you. There, if I go into the merge one, you can see that this is actually exported, loaded from disk, and I'm using a merge node to get that little ball visualized as well. So, and this is it, guys. This is a simple way how you can export out or offload your simulations onto your disk, so you can deal with it much more faster, and there's no much load or stress on your system. And this wraps up my 7-step system for creating destruction effects. I hope you liked it. If you like this sort of content, always commenting something nice, liking, or even subscribing means a lot to me, because it helps me help you. With that said, I hope to see you in the next tutorial. Thank you so much.